In this video, we're going to look at another application of integration in that we're going to look at the regions between curves and the area of these regions between curves. And so let's consider two functions. We have f, that is some upper function here, and g, that is some lower function. And we could consider the area between these two functions on a given interval from a to b. And if we ask ourselves, well, what is that area? How could we find that area? How could we use integration to help us find that area? Well, first, we could examine this the same way we started to examine area by cutting these up into little rectangles. Now, we're not actually going to do that. We're just going to look at it and consider how this is going to help us. So if we cut these up into little tiny rectangles, we see that, okay, let's say we cut it evenly and we find a delta x by b minus a over n the same way. So say we want 10, 15, 20, however many rectangles we want, we can determine delta x. And so the question becomes, well, what is our height? And the height of this rectangle is going to be defined by this coordinate here minus this coordinate here, evaluated at some x value. And so what are these coordinates? Well, these coordinates are taking that given x value for our rectangle and evaluating it in f and evaluating it in g. And to find the distance between those 2 points, we have to subtract those two values. And so really, to find the area of all of this region from A to B, we can simply add up all these rectangles of f of x minus g of x times delta x. And so knowing how this ended up with Riemann sums and how we took these summations and led that into integration, we can use the same idea here to say that, well, the area of a region between two curves is just going to be the integral of f of x minus g of x. And so the nice definition here is that suppose that we have two functions f and g that are continuous, and this is important, they need to be continuous functions, such that f is greater than g on a given interval. Now it's only important that one is bigger than the other just so we have a defined top and bottom function. It doesn't really matter which one's on top, we just need one of them to be on top. And on that interval a to b, and the area bounded by the graphs of f and g on a to b is going to be defined as the integral from a to b of the quantity of f of x minus g of x dx. And so to find the area between two curves, we simply subtract the functions and integrate. It's just like we would before. So look at an example here. Say we have a function f of x is equal to 5 minus x squared, and g of x is equal to x squared minus 3, and we want to find the area that is bound between the two. Now, in this situation, we're not given an interval, so we have to do a little bit of legwork to find the interval, and we have to set these two equal to each other, and we have to ask, when is f equal to g? So that's when x squared minus 3 is equal to 5 minus x squared. And I know I switched the f and the g. That's just because I want to have my positive variable on the left, so it's no big deal. And so we can solve here to get 2x squared is equal to 8. And so x is equal to plus or minus 2. So we see here that the two curves intersect at -2 and +2. Now you can do that algebraically or you can do it graphically, one of the two. You need to be able to do both just in case it's a calculator or non-calculator portion of an exam. And so this tells us our interval. So we know our interval is going to be from -2 to 2. And we want to integrate these two functions, but we don't want to integrate them separately. We want to integrate the difference between the two because we want this area here. So to do that, we can set up our interval. We know it's going to be from -2 to 2, and we're going to have f minus g. And so this will be f of x minus g of x dx. And the important thing is we want to make sure we have the upper function on top. If we don't, we're going to end up getting negative area. And remember, area is positive. It's going to get, we need to have a positive number here because we're talking about the area bound by a curve. So this is going to be the integral from -2 to 2 of f of x, which f of x is 5 minus x squared, minus the quantity of g of x, which is x squared minus 3, and we have that whole quantity times dx, and we're integrating that. So we simplify this. This is going to be the integral -2 to 2. We get 5 minus a -3, so that's going to give us an 8, and then negative x squared minus x squared, that's going to be minus 2x squared. And so when we integrate this, we can find the antiderivative to be 8x minus 2/3 x cubed, and we want to evaluate that from -2 to 2. And so when we put in 2, we get 16, because 8 times 2 is 16, minus 2/3 of 2 cubed, so that's 8. 8 times 2 is 16, so we have 16 minus 16/3, and that gives us 32/3. And then when we subtract, putting in a -2, well, -2 times 8 is a -16 minus 2/3, and then a -2 cubed is still going to be a -8. But then when we add those together, that's going to give us a positive quantity. And so the -16 plus the 16/3 is going to give us a -32/3. So when we subtract -32/3, that becomes positive 32/3, and this gives us a total of 64/3. And so the area of this region here is 64/3. Let's look at another example here, and we have two functions. We have f, that is x plus 3, and we have g, that is the absolute value of 2x. And so we want to know what's the area bound by this region here. And it is a triangle, and so we could try to use geometry here and take 1/2 base times height, but it's going to be a little difficult because we don't have any specific height in the base. You know, it's just going to be kind of tough to do. And so to do that effectively, you'd have to use some trigs. So let's just do the integral. So we need to find, well, where do these two intersect? So you can either do it graphically or algebraically, but let's do it algebraically because, you know, that's more fun. So if we have the absolute value of 2x is equal to x plus 3, that means that 2x is equal to x plus 3, or 2x is equal to a negative of the quantity x plus 3. And so over here we get x is equal to 3, so that's one of the intersection points. And over here we end up getting 3x is equal to -3, so x is equal to -1. So we know our interval is from -1 to 3, and so we want to integrate. Now, here's the tricky part. This function is an absolute value function on the bottom here, the absolute value of 2x. And so how do we treat that? Well, we have to split that up into two functions, because on the left, from -1 to 0, this function is acting like the function of -2x. It looks like a line of -2x, but then at 0, it transitions from here over, it transitions to the function of 2x. So to do this problem effectively, we have to split it up into two separate integrals. So we have integral 1 here, integral 2 here, from -1 to 0 and from 0 to 3, and then we add those two areas together. And so if you evaluate these integrals, we're not going to do it here. I trust that you can do the antiderivative and evaluate. This will give you 3/2 here, and over here we will get 9/2. And if we add those together, those two separate areas, that would give us a total of 12/2, or an area of 6. And so the total area here is in fact 6. And we had to find that by splitting it up into two separate integrals. Now, sometimes it's nice and easy to do it in terms of x, you know, based on the region we have. But there's other times where we have these bound areas that it's much nicer to write our functions in terms of y. We could write x as a function of y, and we have f of y and g of y, and then we can subtract that way. And so we kind of have to change our perspective here, that this area bound is from some value c on the y-axis to another value d on the y-axis, and the rectangle length here that we're looking at is going to be f of y minus g of y. And so we treat it the exact same way, and we look at those rectangles, add up all those rectangles, and we see that, okay, this is just going to be an integral once again. And so we can just say the same integral that we had before, but now it's in terms of y instead of in terms of x. So we treat it the exact same way. It's just a change in perspective a little bit. Instead of going from left to right, we go from down to up. And remember, left to right is a positive integral, down to up is positive. So if we went from a higher value to a lower value, we would have to put a negative out in front. Now, this is an example here of how this could help us. Say we have the function y equals x plus 6, and we have the function y equals x cubed. And so we want to know, well, what is the area bound by these two graphs and the line y equals 0, or in other terms, the x-axis. So we have three things going on here, and to do this effectively with the way I showed you earlier, we would have to look at, well, from -6 to 0, our rectangle is actually bound by the function of x plus 6 and y equals 0. So this would be the area of that region, taking x plus 6 minus 0, evaluating from -6 to 0, and then doing a whole new integral from 0 out to 2. From 0 out to 2, we would have to look at, well, our upper function is x plus 6, our lower function is x cubed. And this works. This is totally fine. You can do it this way, and if this is comfortable to you and you understand it, then go ahead and do it this way. However, it can be beneficial, and later on it'll be more than beneficial. It'll be absolutely imperative that we switch things in terms of x as a function of y. So how would we do this? If this is y equals some function of x, so we need to flip it to say, well, what is x as a function of y? Well, let's just solve for x. So that would turn into x equals y minus 6. So there's our one function, and then to solve for x here, we would have x equals y to the 1/3, or we could say the cube root of y, either way. So the 1/3 or the cube root, they both work. And by doing that, we switch our perspective, and now our rectangles are oriented this way, and we're going from 0 here up to 8, because now, since we're doing it in terms of y, we need to integrate our bounds in terms of y, and now our area is just one simple integral from 0 to 8 of y to the 1/3 minus y minus 6. Now, here's another perspective change. What do we subtract from what? Well, instead of top minus bottom, we want to do right minus left. So what's the function that's on the right? The function that's on the right is x equals y to the 1/3. The function that's on the left is x equals y minus 6. We will continue to practice this a little more in class, and we'll nail down a little more when we want to use y, when we want to use x, and a lot of times you can use either one, just sometimes one can give you a little more of an advantage over the other. Thank you for watching.